Recall that there are two ways by which energy is capable of transferring from one system to another system. So we have work and we have heat. So work is essentially a transfer of energy as a result of an applied force, while heat is a transfer of energy between two systems as a result of a difference in temperature between those two systems. Now there are three different ways by which heat can take place. So we have convection, radiation, and conduction. In this lecture, we're only going to focus on conduction. So thermal conduction takes place between two systems or objects that are at different temperatures and which are in physical contact with one another. So let's look at the following example. Let's suppose we have a spoon and we take that spoon and we place it into a pot. Now, if we take our system of two objects, the pot and the spoon, and place it over an energy source, over a flame, what exactly will take place? Well, an energy transfer will take place. Energy will transfer from our flame into the pot. So the molecules inside the pot will gain kinetic and vibrational energies. They will vibrate more quickly. And these vibrations within the pot will in turn cause the vibrating molecules inside the spoon to vibrate more quickly. And that will increase the temperature of our spoon. So the spoon becomes hot even though it is not in direct contact with the flame because of the process known as thermal conduction. So because the pot, which is in direct contact with the flame, because the pot is in contact with the spoon, there will be thermal conduction between the pot and the spoon. So energy will transfer indirectly from the flame into the spoon via thermal conduction. So conduction takes place as a result of molecular collisions or vibrations between the molecules within our object or system. So let's suppose we have the following experimental setup. Let's suppose we have two objects, object number one that is hot at temperature T1, and object number two that is cold. Let's say it's a temperature T2. Now temperature T1 is greater than temperature T2. So that means because we have a bridge, an object that is connecting our object 1 and object 2, energy will begin to flow as a result of thermal conduction. Now, what exactly is the amount of energy that will flow over some given unit of time across the following bridge? So let's suppose that A is the cross-sectional area of the region through which the energy flows, and it's given by m squared. And this is our cross-sectional area. Suppose the L is the length given in meters of this section through which the energy flows. Let's suppose the change in Q is the energy flow via heat, and that's given in joules, and the change in time is how long it takes the energy to flow, given in seconds. Then we can use the following equation to give us the rate of change of our energy, or the rate of energy flow through the following section. So change in Q divided by change in T is equal to K multiplied by A, where K is the thermal conductivity, and it depends on the type of material, type of object that we're using. So K multiplied by A multiplied by T1 minus T2 divided by L. So notice if our A increases, then the quantity of energy that flows per unit time also increases. Now if the L increases, it decreases. And if the K increases, that implies that amount of energy transfers also increases. And finally, if the difference in temperature between our two objects also increases, if T1 minus T2 increases, the energy flow per unit time will also increase. So let's look at the following example. In a house, a major loss of energy as a result of heat occurs at the windows. Calculate the rate of heat loss in a window 3 meters by 2 meters by 0.003 meters. So this is the height, this is the length, and this is the width. So let the inner temperature be 18 degrees Celsius and let the outer temperature be 0 degrees Celsius. So here we have our window, we have the inside and we have the outside. So energy will flow from the inside to the outside as a result of thermal conduction. So we want to use this equation to calculate the rate of energy loss as a result of thermal conduction. So, we know that our K for glass is 0.84 joules per second times meters times Celsius. This value can be found in a textbook or online. Now, we know the A is 3 times 2, so we have 6 meters squared, and we know the change in temperature is 18 minus 0. So we divide that by the length of our window. The length, or the width in this case, is 0.003 meters, and we get about 30 kilojoules of energy will transfer every single second from the inside to the outside.